So we made it to the last week of instruction. And a reminder that your last exam is exam 3, only on graph theory. It's due on the last day of class. Well, actually, I think I said it to be due next week, but you have till the last day of class to work on it if you want. So let's I hope you guys had a good semester. It was interesting doing this online, but I think it worked out well. So your test is hopefully going to be turned in by the 13th, but if you would like time, you can turn it in on the 21st.
Review.
What was that?
This is Unit 3 review, right?
Yeah, and then that's what we're doing today is like the first part of review 3. Okay, yeah, and today is review 3 for graph 3. We do not meet next week. Just you have time to take your test or visit office hour, but no class. Okay, any questions or concerns? So starting off with what a graph is. A graph is a collection of vertices, each one connected by an edge. Let's break it down to the vertices are the dots. One dot is called a vertex. The lines between the dots are called edges. It doesn't have to be a straight line. It just has to go from the dot, touching that dot, and all the way over to the next dot. And they have to be connected. So that's your edge, xy. You have vertex x and vertex y, or x and y are your vertices. Oh. Okay, and then you can also write yx is the same thing. Next, we want to talk about the degree of a vertex. Alrighty, so we're going to draw a vertex A. This one's going to have multiple edges. 1, 2, 3, 4. It's going to crisscross. This is going to have a loop. So I don't think this came up on the third exam, but we did learn about loops and multiple edges. So when there's more than one edge between two vertices, there are multiple edges. An edge that goes from a loop back, an edge that goes from a vertex back to itself is a loop. So vertices are A, B, C, D, E. Let's find the degree of B. Number of edges that are connected to the vertex. So for degree of B, we did D, E, G of B. We've got 1, 2, 3, 4, 5 edges. Degree of C. So we're here with 1, 2, 3 connections, degree 3. Let's do one more. The degree of D is 2. Okay, let's go to talking about a walk and a path and circuit. And then I think we'll just do a lot of examples after that for those kind of more difficult definitions. So So a walk is a sequence of vertices that are connected by an edge. Like each is connected to the next by an edge. Okay, just a simple x over to y, just straight over to z. So you can go y, z, y, x, that's a walk. So we went this way, came back over that way, and then went over again. Stop. something that is not a walk would be xz. You can't just skip over y. You have to go from x to y and then to z. But x to z is not a walk. Or something a bit more clear would be like, if you have this new example, well, it's fine. We're gonna make basically the same graph, but we'll just add a little extra to this. So let's go make a square shape. And maybe over here, A, B, C, D, E. We're gonna do one that is a walk and is not a walk. So we can go A, D, E, B, E, C if you want to. A over to D, which goes to E. Then I went to B, and I wanted to go back to E and over to C. Okay, something that is not a walk would be like A, C, like skipping over that part right there. And there could be extra to it, but just missing this vertex B is a problem. If you went like A, C, E, D, it's still not a walk. Okay, let's do path. So a path is a walk and you cannot reuse an edge. Or like does not use any edges more than once. So let's find a cool graph. This is we've got basically like a cone kind of shape. This a vertex has two edges between that other vertex. A, B, C. We'll do a path, or let's do a few examples for a path. From B over to C means I'm going to use this one time. I can go from C to A. So it means I've used that edge one time. I can't use it again. And let's go from A to B just once. Could be either of those edges. Just pick this one.
Technically, Professor, could you go from B back to A using the other line?
Yeah,
Or the other edge?
Yeah, I was kind of thinking, I'm going to check the definition because maybe this needs to be a simple graph. So thank you for asking. It's kind of popping up in here too. Let's go to the book. Path. See, because of this. Yeah, it is possible because you can make that trip. It says here, a similar example for a loop, which we'll do next. Okay, we'll try to do that one next. Let's add that in there, that you can go BA, but it's because you have that extra edge to work with. I'll do one more path, like just an easy one, and then let's do this other graph that's from the book. Okay, we're gonna go just BAC. Next example. Okay, there is a loop, and then I'm just going to go straight across. This is called E. Down to D. This crosses over here. And this is going to be called A. Which goes over to B. Let's put C and connect to terms. I think that's good enough. Oh, cool. Okay, so there's first one that the book has goes A, B, C, A, D, E, and then we'll check that out. A, D, A, D, E. So let's travel from A over to B. And then B goes over to C. Either of the edges, doesn't matter. C, wait, A goes to B, B goes to C, C. Hang on, that's not right. I think we're missing something from the graph. Yeah, there's loop over that part. This is connected. Okay, well, there's supposed to be, the book has a better drawing, but there's a connection between A and C. So we can do this still. A goes to B, over to C, C to A from that line that I just forgot to draw. A to D, that way. D to E. So that was a path. The next one they have in here is ABC ADE. ABC
That's the
ADE.
one we have up above, Professor.
I still have some more though. ABC ADE, and then it goes EB.
Oh, sorry.
It's cool. It's cool. We're gonna check this one out though, because this one had a little extra note. It's about the loop, I can tell. So A to B, B to C. And yeah, we've done this a little bit. So C to A is on this side here. A over to D. Oh, so we're just continuing that a little bit. We're gonna go DE, and then a little extra E around the loop. E to B. I was about to say this looks like an Euler path because I felt like we used all of the edges, but we didn't use that edge right there. So it's just a path. We used each edge one time as we made this trip. Let's see what else is in here. Okay, let's jump. We're going to use the same graph, but we're going to jump to finding a circuit. So, a circuit is a ends where it starts, or starts where it ends. It's going to be the same graph. I just feel like everything's gotten kind of messy, and I'm going to try drawing this over. Okay, should be everything. So we have ADEBA.
Professor, is the other end of the, or like the unlabeled one, is that supposed to be C?
Oh yeah. Thank you. ADEBA. So we're just going to make sure that that is a circuit. Going from, like, just because it starts at A and ends at A, you need to make sure you only use every edge one time. From A to D. D over to B. Wait, D. It's supposed to be an E. I wrote it wrong. These are in the wrong spots. The way it was before wouldn't have been a circuit or path or walk. It would have been just none or like in the test, you could say like neither of the options. Okay, from A to D, D goes to E this way, E to B, B to A. So I started at A, ended at A, and I used every edge one time. Let's go on to BCB. From B, pick one of them to get to C, pick the other one to go back to B. Anything else? Oh, one more, EE. So start at E and go around the loop to get back to E. So we've done block and path and circuit. Let's talk about the Euler paths and Euler circuits. Euler path is a path that uses every edge. Or like visits every edge. And an Euler circuit is a circuit that visits every edge. So I thought, just popped in my head that I've mentioned before that with your paths and your circuits, it is okay to reuse or revisit a vertex. You just cannot reuse or revisit any of the edges. So, and that's the same for Euler paths and Euler circuits. So paths, circuits, Euler paths, and Euler circuits. To reuse a vertex. Or vertices if you have that happening a couple of times. they cannot reuse an edge. Or any edges. Okay. And that should be the end of all of the definitions we did and all of the information you need for your test. Now it's just up to us doing lots of examples. Today, I'm going to look in the book. This one. It takes a map and changes it to a graph. And then we're going to see if we can find an Euler path from the graph or an Euler circuit. So we have there's multiple edges from here to here between L and A. And it happens again between A and R. Then there's going to be a swoop over to D, which goes around and over, but it's just, you know, doesn't need to be like that. It could be smooth. Cool. And then there's a connection from A to D. So the question was, like, can a person travel across or travel through the map and visit every edge one time? So can a person find an Euler path? So what this is asking is, can an Euler path exist? I just realized that there's two results that are useful, so we want to write those down, and then that's all of the stuff that we really need for the test. So the trick was to look at the degree of your vertices. If there are two odds, then you've got an Euler path. If there are no odds, you can find an Euler circuit. But if you don't have either of those options, then you can't find either of those choices. Okay, let's give this problem a try first, and then I'll get those theorems up after. So check the degree of your vertices. This is degree 3. Degree 3. Also degree 3. And that's 1, 2, 3, 4, 5. Okay, I have more than 2 odd vertices, so it's not going to have an Euler path or an Euler circuit. So if you can't find an Euler path, then you definitely can't find an Euler circuit because it's a path that uses every edge, and the circuit part means you start where you end. So it would be like an extra requirement that we can't meet. Okay, first theorem was for finding a path. If you have two odd vertices, you will be able to find an Euler path. If there are 0 odd vertices, an Euler circuit exists. Maybe let's put like no odd. If there's more than 2 odd, like this one here, there's 1, 2, 3, 4 odds, neither an Euler path or Euler circuit exists. Cool. Okay, so let's see what's in the book. Let's try this one. So this is a little piece of a map. It says that a driver is trying to find a route in which they visit every street once, starting and ending points, and having the starting and ending points being the same. Okay. First, let's get that map down. Looks like go from here, just kind of straight over, one more time. And this one goes down at an angle and over, and that just kind of stays there at the end. Back, connect, goes back again. This, we will add one more square and then just kind of stop. So a driver wants to deliver packages down every street, wants to visit each street one time, or just doesn't want to make extra trips. So just a little extra piece is that they want to make each trip one time, or how do we say this? In a single pass. Okay. I'm just going to write it all out without revisiting any streets. So. Okay, so first, what are we looking for? We're looking to start where we end. So we want a circuit. We want to visit every street, so we need an Euler circuit. So we want to check all of the degrees and see if they're all even, or just make sure that there's no odds. And then this is possible. But if we find even like one odd vertex, it's not possible. We can just stop. Oh, well, right there, that's degree 1. So there's an odd degree. And so I could just go ahead and stop. I found one odd vertex. They're not all even. So it's, my answer would be an Euler circuit does not exist. Does not exist. But just for practice, let's go ahead and label the whole graph. So this is degree 1, degree 2. There's a 2. On that side is degree 1, degree 2, degree 1, 2, 3, 4, 3, and that should be everything. Okay, let's just do one more, and then next time we'll just do examples for the whole class. Ew. Whoa, this is cool. Okay, so the only requirement I want to add to finding Euler paths and circuits is that it does need to be a connected graph, but you don't have to really worry about that. And just, I gave you connected graphs on your test, but it means it's a graph that's in one piece. So the next graph is just one piece. We're going to go kind of create a big hexagon shape. Oh, there's a vertex right in the middle of this. Here, over. And then there's a vertex there, and there. And then we're going to put multiple edges with some right here, and down here, and then to the sides. Flower kind of shape. Let's see if we can find an Euler path or Euler circuit. So we're going to check degrees, and Euler path is when you have two odd. Euler circuit is when there's no odd. Otherwise, it's going to be neither. Let's do degree 2. So we're off to a good start. So we already got an even. This looks like it's 1, 2, 3, 4, 5. So if I find more than 2 odds, I won't have an Euler path. But I know that with this one odd vertex, there's no Euler circuit. Okay, let's keep going. Degree 2. That's okay. This is another one, I think. 1, 2, 3, 4. So that's all right. Let's go to the side. Is this another 5? 1, 2, 3, 4, 5. Okay, so I've got 2 odd. If I find one more, then I've got to cross this one out too. This is a 2. So 1, 2, 3, 4. There's a 2. So it's this middle one that I'm worried about. If it's odd, then we don't have an Euler path. But if it's even, then I can find an Euler path from that graph. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just going to double check. Start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great, so there's exactly 2 odds. Those 2 on the sides, which means I can find an Euler path. Just gonna look at what their homework looks like, but I feel like we've done good for today, and we're probably just going to do examples next time. Yeah. Whoa. Yeah, we'll save these for next time. They're pretty cool pictures, and we'll just spend some time drawing all of these graphs and trying to apply as much practice to them as we can. So thank you for coming to the meeting. Have a good week studying for your finals. We'll see you on Thursday for our last meeting.